Hey everybody, it's Jen from Norman S. Wright. It's November and we started talking about heating last week, so let's keep that theme going. This week I want to talk about electric reheat on VAV boxes. So let's get started. Electric coils are made up of an element wire that heats up when it's powered. As the supply air passes through the electric heater, the heat is transferred to the air and into the space. When the space is below set point, the controller calls for the heat to turn on. The most common elements are open coils. They look kind of like a coiled wire, just like in your toaster. They're made up of 80-20 nickel chromium wire. You'll also see thin tubular electric heaters, which have an element centered in a stainless steel tube filled with magnesium oxide and surrounded by stainless steel fins. Let me make a little bit more room to draw this. So it'll kind of look like this. The element would be inside this tube, and these are the fins. These are more expensive, but they're also more durable because they're resistant to dirt, dust, and moisture. Let's make a little bit more room again. Electric coils are almost always mounted on the discharge of VAV boxes because the element wires need to have some airflow whenever they're energized so they don't overheat. And then this little dashed line is the control box that would be on the outside of the unit. Because you have to have good airflow, you need to make sure the coils are far enough away that they get good airflow across the entire face of the coil. Electric heaters have an airflow proving switch so that the heater will not turn on if there's not airflow. So inside your control box, you'd have an airflow proving switch that is piped to a pickup point to measure whether there's airflow or not. The airflow switch works off of differential pressure, and it needs at least 0.07 inches of pressure between the inside and the outside of the unit to close the switch. Fan power units will also have a fan relay that won't let the electric heater turn on unless the fan is running, so that it can guarantee airflow. There will also be thermal cutouts to shut the heater off if it gets above a certain temperature. It's been a while since I looked at the code, but I think that temperature was a 200-degree Fahrenheit max. Electric heaters have to have an automatic reset thermal cutout, which will reset when the temperature drops below the cutoff temperature. You can also get manual resets that will require someone to go and push a button to reset the thermal cutout, and then that way someone has to go to the unit to reset it and hopefully find out why it tripped. Let's scoot this over again. Electric heaters also have a high free area, so they have a low pressure drop. Now, I've been talking about integral VAV box electric heaters mostly here, but this pretty much applies to standalone duct heaters as well. With standalone duct heaters, you'll see slip-in heaters and flanged heaters. Slip-in heaters look kind of like this, where there's a hole cut out of the ductwork and the heater will slip into the side of the ductwork. Flange units kind of look like this, where the ductwork is in two sections and the edges of the heater and the ductwork are flanged so they can all be mounted together, and the heater is put between the two sections of ductwork. Let's move this out of the way again and talk about heater control. There are two main types of heater control: staged heat and SCR heat. Staged heat turns the heat on in stages, usually 1, 2, or 3 stages. A single stage electric heater turns all the heat on at once. A 2-stage electric heater turns 50% of the heat on in stage 1 and 50% in stage 2, and so on with 3-stage, 4-stage, and on. So if we have a 10 kW heater with 2 stages and a room set point of 75 degrees, let's kind of draw what this looks like. So let's say the first stage is going to be 5 kW, the second stage will be the second 5 kW, giving us 10 kW total heat. If you start with a room in the morning, maybe it's 72 degrees, it calls for heat, turns on the first stage, so 5 kW comes on. I didn't really do the math here, but let's say that only takes it up to 74 degrees, and so the second stage will turn on, and now you have 10 kW. But now it's too hot, and maybe it gets to 78 degrees in the space, and so the heater is turned off, and then the temperature drops again, and when it gets to 73 degrees in the space, it turns on the first stage of heater, which gets us back to 74, and on like this. So you can see in this situation, you will be a little too cold or a little too warm on and off all day long. SCR heat solves the problem of overheating and underheating by matching the heat requirements in the space. SCR stands for Silicon Controlled Rectifier. In reality, SCR heaters aren't actually SCR controlled anymore. They've been replaced by SSR heaters, solid state relay heaters, but the name is stuck around and we still call them SCR heaters. In an SCR heater, the on-off signal that energizes the elements pulses on and off over a set period of time, usually a couple seconds, to provide the exact amount of heat needed. So for instance, if you need 50% heat, the heater will pulse on half the time and pulse off the other half the time. So say 1 second on and 1 second off. So if you have a 10 kW heater in that space we had earlier, and maybe we needed 7.5 kW equivalent of heat, or 75% of that heat to be on to get us to the set point, then the heater is going to pulse on 75% of the time and modulate to maintain this set point throughout the day. So I'm going to end with a little bit of math that's helpful to know. The first one is that kW equals CFM times delta T divided by 3160. This allows you to calculate the kW you need to get the temp rise you want at a given CFM. So for instance, if you have 400 CFM of 55-degree air and you want 95-degree leaving air temperature off your coil, then you can do the math here and go 400 times 40 degrees temp rise, which is 95 minus 55, divided by 3160 is about 5 kW. You can also use this equation to calculate the temp rise if you know the kW and CFM, or the CFM if you know the kW and the temp rise you have. You can also calculate the amps if you know the voltage in kW. So for single phase, the amps equals kW times 1,000 divided by the voltage. And for three phase, the amperage equals kW times 1,000 divided by the voltage times 1.73. So if we have a 12.5 kW heater at 120 volts, that comes out to 104 amps. That same 12.5 kW at 480 volt, three phase, is 15 amps. So let's bring all of this back on screen. That covers basics of electric heat. Don't forget to like and subscribe to our YouTube channel, and thanks for watching.